Hi guys, I am so sorry for how long this video has taken to come out. I have had the worst 2 months in, well, not in my life, but certainly in my recent history. I will produce a video after this is over explaining in detail what happened, but suffice to say, I have a new computer now, and a lot of people to thank for it because I wouldn't have been able to get one on my own.
Anywho, um, I hope you find this year's list interesting. As per last year's list, this is a very personal selection, and while I've tried to pay heed to what others have considered important, this is still very much my own opinion, so hope you enjoy it.
Water on Mars. Again. It seems that whenever we discover water on Mars, we allow it to take us by surprise. In actual fact, we've known that Mars has water since 1956, when Gerard Kuiper caught its spectrum in the planet's polar cap. This year, though, Mars was so determined to remind us of its water that I half expected Olympus Mons to turn into Hawaii. Perhaps the single most knee-sagging reminder this year occurred in July, when ESA's Mars Express, which has been in orbit around the planet since 2003, used ground-penetrating radar to detect a subsurface pool of liquid water at least 1 meter deep and 20 kilometers long underneath Mars's southern polar cap. Now, you might be thinking, why didn't they discover this in 2003? Well, up until now, evidence from the radar instrument had proven inconclusive, but by way of some inventive hacking to bypass some of the onboard computer's excess processing, the radar team managed to jack up their resolution to the power needed to see the lake. Technically, this is the first body of standing water ever discovered on the surface of another planet. And yet, in this age of plumes on Enceladus, methane lakes on Titan, and innumerable water-world exoplanets, it feels a bit late to the party. In other wet Mars news, this November, in a paper in astrobiology, Henrik Argetai and colleagues analyzed outflow channels of the Hellas Basin, a gigantic impact crater that is one of Mars's defining landforms. They determined that the channels must have been home to up to 34 lakes. Not only did these lakes have different sources, such as rivers, groundwater, and even snow, but they formed in different times across Mars's history, and thus Mars must have had liquid water on its surface for an extended period of time. The project identified 34 potential dry lakes, one of which bears a striking resemblance to a salar, a form of saline lake found in the Andes, meaning Mars would have had a similar climate to a high, mountainous region on Earth. In December, Mars Express caught this image of the permanently iced Korolev crater, which lies above Mars's Arctic Circle. The crater, named after Sergei Korolev, the mastermind of the Soviet Union's early space program, is exceptionally deep, which means ice remains frozen longer at the bottom, keeping the air above it cold. This cold air then acts like a shield, keeping the ice frozen year-round. The cap is estimated to be about 1.8 kilometers deep, making it comparable to several ice sheets on Earth. Oh, Oumuamua, you got moves. If I'd made a best-of-year video for 2016, Tabby's star would have topped the list. You all remember Tabby's star? That outwardly unassuming star hidden in the backwaters of the Kepler catalog that turned out to have an orbiting structure so bizarre that no one could explain it? Well, I'm afraid to say that, at least in this case, it isn't an alien megastructure. Studies in October this year showed definitively that whatever is orbiting Tabby's star is blocking more infrared than ultraviolet light. In other words, it cannot be opaque, or it would be blocking all light equally, and thus it can't be larger than dust particles. This year, the big alien kerfuffle seems to revolve around fast radio bursts, but FRBs weren't discovered in 2018, and the whole ET shenanigan really began brewing in 2017. No, for this list, I'm afraid I must hand the Is It Aliens medal to last year's winner. Oumuamua, which in 2017 whizzed around our sun from somewhere near the current location of the Vega system, so fit the expected profile of an interstellar spacecraft that the current giant SETI project, Breakthrough Listen, scanned it for signals. This year, Marco Micheli and colleagues published an article in Nature showing that somehow, despite moving farther from the Sun, Oumuamua was speeding up. After ruling out light pressure, drag, friction, magnetism, and geometric effects, Marco and friends determined that the only logical explanation was that Oumuamua had to have outgassed, creating jets of material that pushed it forward. But there was a problem. If Oumuamua had outgassed, then it was a comet, and while it was certainly covered in enough tarry carbon gunk to be a comet, it hadn't demonstrated any outgassing when it was close to the Sun, when you would have most expected it to. In November, Shmuel Bialy and Abraham Loeb of the Harvard Center for Astrophysics offered this in response. Oumuamua could have accelerated due to the Sun's light pressure, provided it was less than a millimeter thick. In their paper, they outlined that such an object, despite its flimsiness, could have survived any interstellar journey shorter than 10 kiloparsecs, which is about 3,000 light-years. And then the paper achieved fame. In the conclusion it stated, quote, "If radiation pressure is the accelerating force, then Oumuamua represents a new class of thin interstellar material, either produced naturally through a yet unknown process in the ISM, that is, the interstellar medium, or in protoplanetary disks, or of an artificial origin." Unquote. Specifically, the paper argues that Oumuamua is a light sail, a romantic form of spacecraft now being tested that employs light pressure from the Sun the way the sailing ships of old used wind. And not only could it be artificial, the paper argues, it might even be deliberately targeted, because to argue it was random meant that there would have to be hundreds or even millions of times more material between stars than predicted by models. The paper caused a sensation. Scientists, as you might expect, reacted with some skepticism, but Loeb was undeterred. In a cheerful article in Scientific American, Loeb argued, given that technologically mature societies like ours inevitably destroy themselves, Oumuamua might be the broken relic of a long-dead civilization. No offense meant, but speaking as someone still harboring dreams for the future, I hope he's wrong.
Primordial Titans.
Nothing in the universe astounds me more than the human capacity for boredom. In the 1920s, when the sheer scale and eon-spanning age of the universe was first understood, the shock was enough to send people like H.P. Lovecraft screaming for the covers. He and his followers envisioned increasingly vast cosmic structures beyond any human comprehension, older than the earth and indifferent to man, spanning the frigid black abyss in their terrifying majesty. Today, we routinely shrug off documentaries as they insistently remind us that the Sloan Great Wall is more than 1 billion light-years across, or that Laniakea, our home galaxy supercluster, comprises a mass of 100 quadrillion suns. It seems Lovecraft was wrong when he claimed that we would all go mad from the revelation of the true nature of reality. We have a built-in firewall against the horror of our cosmic insignificance. We ignore it. Which is why I like it when the door to the total perspective vortex jams open a few inches and gives our complacent brains a chance to squirm. One thing that most people know but don't often take on board is that when you look out across the immensity of space, you are also looking back in time. When you see an object billions of light-years away, you are seeing it as it was billions of years ago. So a telescopic image is like a core sample of the universe, each farther image revealing an earlier phase of the universe's evolution.
And of all the elder things dredged from the ebon mists of the universe's past this year, none force me to question my own assumptions more than Hyperion.
From the Hubble Ultra Deep Field, I'd always assumed that the early years of the universe were when the Lego was still just out of the box. Tiny, malformed galaxies, just waking up, yet to be organized. But this year, Olga Cucciati and colleagues at the European Southern Observatory's Very Large Telescope in Chile identified a truly gargantuan structure at a redshift magnitude of 2.45, which means it must have formed just 2.3 billion years after the Big Bang. This structure, dubbed Hyperion, is gigantic, of a mass comparable to the Laniakea supercluster. Thanks to the VLT's VMOS instrument, which allows for the plotting of multiple galaxies at the same time, the team were able to map the object in 3 dimensions, and they found that, while big, it was somewhat flabby. Modern superclusters are trim, tight, and wiry, with their mass concentrated in compact nodes and sinewy filaments. But this creature comprised a series of vaguely defined connected blobs of weakly associated galaxies, indicating gravity had had less time to shape and sculpt it. And that wasn't the only discovery made by the VLT this year. In October, whilst examining the Hubble Ultra Deep Field, its spectrograph drew something beautiful out of the cosmic darkness. The universe is glowing. It has often been said, mainly by me, that the universe is what happens when hydrogen is thrown into a bucket called gravity. It's a gross oversimplification, of course. A single hydrogen atom is already an almost incomprehensibly complex structure, deep enough to contain entire fields of physics. One of these fields is quantum mechanics, and one of the effects of quantum mechanics is the Lyman series. Without being too technical, because I barely understand it, the Lyman series is a scale of increasing frequency light flashes that occur when the electron of a hydrogen atom is excited into another level. The first level is called Lyman alpha, the second Lyman beta, and so on. The Lyman alpha emission leaves a specific mark in the ultraviolet spectrum, and astronomers are very familiar with it, since it occurs whenever light from the distant universe passes through clouds of hydrogen gas, a fairly common event, as you might imagine. Indeed, astronomers often speak of making their way through the Lyman alpha forest, one of those strikingly poetic turns of phrase that I wish scientists would make more often. And this year, when a team of astronomers turned the VLT's Muse spectrograph toward the region of space covered by Hubble's famous ultra-deep field image, they found the ancient galaxies aglow with Lyman alpha light. It seems that in their earliest days, galaxies were enshrouded by cocoons of hydrogen that their stars illumined like city lights in fog. And if this light is present in the Hubble Deep Field, that means it must be present across the sky, hidden behind the light of more recent history, a soft glow from the dawn of time. Another relic from the time of creation was identified in August by the Lausanne Polytechnic's aptly named Pristine survey, which aims to scan the galactic halo for some of the oldest and most metal-poor stars in the universe. If you watched my video on Barnards Star, you'll know that metal is astronomese for any element heavier than hydrogen and helium, and that a star's metallicity is an indication of its age. The older a star is, the lower its metallicity, and the galactic halo is home to some of the oldest stars known. The ultimate dream of projects like this is to locate so-called population 3 stars, stars that formed out of the primordial mist left from the Big Bang. If they exist, they are so far beyond our sight that they are likely to remain unseen until, or unless, the James Webb Space Telescope begins operations. These stars are also known as megasuns, as their pure hydrogen-helium composition allowed them to grow to monstrous sizes. However, since large stars live fast and die young, they would have barely lived a few million years before tearing themselves apart in supernovae. It was the deaths of these virgin stars that seeded the universe with the material for planets, soil, and life. Pristine 221, as this relic star is known, is not a population 3 star. It couldn't be, since one so close to our home galaxy would be long dead by now. But it is the closest we have ever found. Its metallicity value is minus 4.66, making it roughly 50,000 times less metal-rich than our own sun. But what truly astounded was the star's near-complete absence of carbon. Its carbon score was 5.6, or nearly 1,000,000 times less than the sun. Astronomers are frankly baffled by this. Carbon is one of the easiest elements for stars to create via fusion, and its presence was thought to act as a necessary cooling agent that allowed pre-stellar gas clouds to calm down enough to form into stars. And it isn't the only ultra-carbon-poor star found. Another ultra-metal-poor star was located in November, this one not in the ancient halo, but in the relatively young disk in which our own sun resides. Clearly, there is much still to be learned here. Life is strange. But how strange? The famous assertion of Carl Sagan that we cannot be alone in the universe rests on one fundamental assumption, that our solar system is normal, which, with a sample of 1, is a solid assumption to make. Except we don't have a sample of 1 anymore. Thanks to Kepler, we now have several thousand multi-planet systems to choose from, and that sample was beginning to make our solar system seem like a dowdy eccentric. For instance, it turns out that the familiar pattern of smaller rocky planets farther in, giant gaseous planets farther out, which we'd assumed would be the norm, is decidedly not. Many gaseous planets found to date are within the orbit of Mercury and are known as hot Jupiters. Also, planets in other systems tend to be of the same size and evenly spaced, like a string of pearls, rather than exponentially spaced and of wildly different sizes as they are in our solar system. This has lent some credibility to the rare Earth hypothesis, the idea that in order for us to be in it, our solar system has to be peculiar, meaning that life, and in particular intelligent life, is likely rare in the universe. But hold on, normal doesn't have to mean boring, and there is no reason a perfectly normal planet can't be as lively as our own, as this year proved many times. In October, a team led by John Michael Brewer at Yale trolled Kepler data to discover that compact multi-planet systems are likely to form around low metallicity stars. Since planets are made of elements heavier than hydrogen and helium, it had long been assumed that planets were more likely to form around younger, higher metallicity stars like our own Sun. Except we've been finding planets around low metallicity stars left, right, and center. And now we know that small, compact systems, kind of like our own inner solar system, are likely to form around them, which means they may represent the earliest examples of solar systems in the universe. Such worlds have had plenty of time to evolve, maybe even to evolve life. One surprising finding in the Kepler dataset is that planets larger than the Earth but smaller than Neptune are not only more common in that sample than planets the size of Jupiter, they're also more common than planets the size of the Earth. These super-Earths, apparently absent from our own solar system, unless, of course, Planet 9 is real, are ridiculously common in the galaxy as a whole. In August, a team led by Li Tseng at Harvard used mass data from ground-based observations and radius data from Kepler to determine the densities of dozens of planets, and concluded that these super-Earths with radii above 2.5 times that of Earth were likely to be mostly composed of water, much like their slightly larger analogs in our own solar system, Uranus and Neptune. The study concluded that these water worlds should comprise up to 35% of all exoplanets larger than Earth, but these could not be habitable, surely. Their liquid inner surfaces would see temperatures of up to 500 degrees Celsius, while their inner cores would crush any water into exotic forms of ice. Well, as of June this year, they do have one thing in their favor. It had long been thought that a water world could not possess a carbonate-silicate cycle, the process in which Earth stabilizes the amount of carbon dioxide in its atmosphere and ensures that it doesn't go the way of Titan or Venus. But models run by Amit Levy of the Harvard Center for Astrophysics have shown that if a water world is rotating at about 3 times the speed of Earth and has a carbon dioxide level high enough, the world may form a mineral-rich polar cap that will rise and sink, creating an analog to the carbonate-silicate cycle. Additionally, a study by Edwin Kite and colleagues found that even a water world with an ocean 100 miles deep, where water has completely cut off volcanoes from the atmosphere, could still cycle carbon, provided its oceans were not too loaded with minerals that could react with carbon dioxide, pulling it into the depths. One of the major arguments of those in favor of the rare Earth hypothesis was that plate tectonics, a process so far only known on Earth, was necessary for the evolution of life, because it maintained the cycle of carbon released into the atmosphere, buried in rock through weathering, and then transported into the mantle by plate subduction, only to be released again by volcanism. This cycle keeps carbon dioxide levels on Earth stable, moderating its climate. But in July, geoscience researchers Bradford Foley and Andrew Syme modeled the carbon cycles on single-plate worlds, known as stagnant lid planets, and found an alternate path to a carbon cycle. Volcanoes on stagnant lid planets are shorter-lived, but unlike volcanoes on tectonically active worlds, they remain in place, erupting over and over on the same spot. On Mars, this process, coupled with lower gravity, has led to the formation of gigantic peaks like Olympus Mons. As lava piles on lava, heat and pressure increase, leading to the release of CO2. Another rare Earth hypothesis, reinforced by the terrestrial planets in our own solar system, is that only those with a fluid iron core could generate a magnetic field strong enough to preserve the atmosphere from the force of the sun. However, this might just be a lack of imagination. Most of a planet's interior is composed of forms of silica, or rock as we call it. Silica is not a substance known for conducting electricity, but in July, Bradford Foley and Andrew Syme calculated that a super-Earth several times the mass of our own produced pressures and temperatures at depth great enough to slightly electrolyze silica, generating a field about 1/100th the strength of iron, but still capable of producing an Earth-like field if the planet's rotation were faster than about 2 days. What are little planets made of? One question that has bedeviled the search for extrasolar habitable planets is where exactly the dividing line lies between a large rocky planet like Earth and a small gassy planet like Neptune. In October, a team led by Michael Lazowski of the University of Zurich employed statistical tools to calculate the threshold radius for a planet's composition. The team found that planets up to 1.4 times the radius of Earth could still be Earth-like in composition. Planets between 1.4 and 1.6 Earth radii had a less dense, higher silicate composition, while planets above 1.6 Earth radii had to contain a substantial portion of lighter elements, or ices. Planets above 2.6 Earth radii had to contain at least some hydrogen and helium, with the amount increasing to as much as 10% at 4.3 Earth radii, which corresponds to a size and composition similar to Neptune. A separate study, also by Li Tseng and colleagues, showed that exoplanets did not increase steadily in size, but had pronounced gaps or deserts in their determined radii, particularly at 2 Earth radii and 4 Earth radii. The gap between 4 and 10 Earth radii, dubbed the sub-Saturnian desert, suggests that the transition point between the gas giants above and the ice giants below is very seldom inhabited. The team concluded that these planets below 2 Earth radii could be called rocky, those between 2 and 4 Earth radii could be called watery or icy, those rare examples between 4 and 10 Earth radii could be called transitional, and those above 10 Earth radii were gas giants. In February, teams of astronomers at the Carnegie Institute for Science tested a variant of this idea on the star system GJ9827, which happens to contain 3 planets just straddling the size boundary between rocky and gassy. GJ9827b has a radius of 1.64 times Earth's. C's is 1.29, while D's is 2.08. Thanks to some very thorough spectrograph analyses, the teams were able to constrain the 3 planets' masses, and frankly, they were a bit wonky. D's mass was determined to be about 4 times that of the Earth, which is roughly in line with its radius. C, the smallest of the group, had a mass 2.5 times that of the Earth, while B, at just 1.64 Earth radii, was a whopping 8 Earth masses. That meant that B had to be one of the densest planets known, likely made mostly of iron. D almost certainly had a gassy envelope of some kind, but the team didn't observe it. So remember, people with telescopes, the universe is under no obligation to conform to your expectations. Life. But do we know it? Abiogenesis, the formation of living matter from non-life, is one of the great remaining black boxes in our 300,000-year quest to place ourselves in the universe. So far, we've found plenty of construction material, in the form of amino acids, sugars, and precursors to genetic molecules, scattered throughout our solar system and beyond, and plenty of results, with the discoveries of ancient bacteria in the harshest environs of our planet, and genetic mapping allowing us to trace our ancestry back to a single, tiny, simple cell 3.8 billion years ago. But that little moment of self-organization, when a bit of tar suddenly became one of the most complex machines ever observed, still eludes us. Which means that determining how life could form on other planets requires embracing certain assumptions. For example, in August, a team of researchers at Cambridge, drawing on studies originally performed by the Medical Research Council, identified a number of planets as potentially habitable based on the amount of ultraviolet radiation received from their stars. In 2015, a study by the Council argued that carbon from meteorites reacted with nitrogen in our atmosphere to form hydrogen cyanide, which then used UV radiation from the sun to form the building blocks of RNA, widely regarded as the first genetic material. The group recreated these reactions under a UV lamp and found that they produced not only the precursors of RNA, but also those of lipids, the building blocks of fats, and amino acids, the building blocks of protein. It just so happens that stars like our Sun produce just the right amount of UV to power these reactions. Of course, this might be just another bit of rare Earth terracentrism. The head of the group, Dieter Kielos, one of the first two astronomers to observe an extrasolar planet around a Sun-like star in 1995, was careful to point out that these same reactions also occur in the absence of UV light, but at a far slower rate. In June, an interdisciplinary team of researchers at NASA's Nexus for Exoplanet System Science compiled a list of likely biosignatures we might be able to detect on other planets from our own. While focusing on the signatures meant for ourselves, the speculation was admirably open-ended, exploring ideas like alternate forms of photosynthesis, particularly around red dwarf stars, and the possibility of biosignatures in non-oxygen dominant atmospheres. But as they point out, free oxygen in the atmosphere remains the best biosignature by far, since oxygen is so reactive that without regular replenishment from, say, plants, it would quickly rust into the ground. At least, that's the theory. The team did admit that free oxygen could be produced by abiotic processes, such as the breaking down of CO2 and water by strong sunlight. In December, Chao He and colleagues ran experiments to see if they could recreate a series of potential extrasolar planetary atmospheres in a lab. Hydrogen-rich, water-rich, and CO2-rich at 200, 400, and 600 K, and found that when exposed to simulated lightning or UV radiation, several scenarios produced free oxygen on their own.
This does not rule out oxygen as the prime biosignature. As far as I can tell, no abiotic process can produce an atmosphere as rich and abundant with oxygen as our own.
Mooning. It's rather strange that despite nearly 30 years of exoplanet discovery, we haven't found an exomoon yet. After all, we've found exoplanets the size of Mercury and even exocomets. Why not exomoons? Well, this year, we just might have. In October, geoscientists Alex Tichy and David Kipping reported the discovery of a large object orbiting another large object orbiting a star, Kepler 1625 to be exact. The orbiting object, Kepler 1625b, is roughly 10 times the mass of Jupiter, which is why I keep referring to it as an object rather than as a planet. You see, according to current definitions, an extrasolar planet isn't a planet if its mass exceeds 13 times that of Jupiter. Why this seemingly arbitrary distinction? Because any larger and the planet starts to fuse, and we can't have that. More precisely, it begins to fuse deuterium, a heavy isotope of hydrogen, making it something not strictly a planet and not strictly a star, which we call a brown dwarf. So this planet may not be a planet at all, but just another low-mass star in a binary star system, which would in turn mean that its moon is not a moon, but a planet, which would be a relief because calling this monstrosity a moon violates my sense of cosmic decorum. You see, this moon, called Kepler 1625b1, is the size of Neptune. Moons should not be the size of Neptune. I don't want ants the size of cars, and I don't want moons the size of Neptune. Ah, but the planet is 10 times Jupiter's mass? Well, fine. Give it a moon 10 times the mass of Ganymede. Or even a moon the mass of the Earth. I don't care. Just keep your Neptune-sized moons away from me. The odd thing here is that I know I don't have a leg to stand on. The mass ratio between these two objects is almost exactly the same as that of our own insane planet and its equally mentally ill moon. Kepler 1625 is slightly larger than the Sun, and its planet, or companion star, orbits at roughly the orbit of Venus. That means that this moon, or planet, is probably not in the star's habitable zone, which is a shame because observations suggest that the moon, or planet, may have a moon-moon. Yes, that is what they're called, that you could actually stand on. Assuming, of course, that it actually is a moon-moon and not just, a moon. And speaking of moons that would be planets in any sane universe, so much has been made, and rightly so, of Titans' rain and flowing rivers, that it is sometimes hard to remember that it is, at heart, a desert world. The vast majority of its surface is given over to rolling, coffee-colored dunes of tarry sand. so it shouldn't really come as a surprise that it would behave as a desert would. And this year, analysis of Cassini data from 2009 to 2010, near the moon's spring equinox, has found evidence that, much like our solar system's premier desert planet, Mars, Titan erupted in dust storms, except Titan isn't Mars. Its atmosphere is 100 times denser, even denser than Earth, and generating dust storms requires surface wind speeds 5 times faster than models predict exist. In fact, the only thing known to be capable of generating such winds would be a methane rainstorm, which are believed to have occurred at the same time as the dust storms. So perhaps Titan isn't so much of a desert after all. In more disappointing news, in October, ALMA, the Atacama Large Millimeter Array, a troop of radio telescopes staring out from the driest desert on Earth, released the first ever full thermal map of Jupiter's moon Europa, and it was boring. Just a reflection back of what would be expected from albedo and surface features. For a world believed to be home to a churning ocean and underwater volcanoes, this was a decided underachievement. Another study this year found no evidence of thermal increase at the sites of possible plumes. Europa, when are you going to stop leading us on and just tell us one way or the other? Our home gets bigger. One of the few statements consistently made by both scientists and the media that I would call an outright lie is whenever you hear that such and such a spacecraft has left the solar system. In my lifetime, the Voyagers have left the solar system 3 times. Once when they crossed the distance to Pluto, once when they reached the heliosheath, the turbulent region marking the edge of the solar wind, and once when they finally crossed the heliopause, the point lying at around 120 AU, or Earth-Sun distances away, at which the solar wind finally gives out to the winds of interstellar space. Many will say that the Voyagers have, at long last, left the solar system for good. Do not believe them. The Voyagers may be outside the range of the solar wind, but the solar wind does not define the solar system. The sun's gravity does, and it is calculated to remain dominant over the gravity of other stars to a distance of 2.4 light-years, or more than halfway to Alpha Centauri. By the time the Voyagers cross that line, Earth will be pointing at a new pole star. I think this reticence to reveal the solar system's true gargantuanness to the public at large may be due to a desire not to make our home system, or worse, the amount we actually know about it, seem insignificant. If Planet 9 is ever found, you can expect that reticence to fade into irrelevance. And speaking of Planet 9, in October, Scott Shepard and Chad Trujillo, veterans of Mike Brown's epic planet quest that led to the discovery of Eris, announced the discovery of 2015 TG-387, which they, in light of its initials and the spookiness of the month, nicknamed the Goblin. The Goblin is truly a mooncalf of a creature. With a diameter between 350 and 400 kilometers, it hovers just under the boundary of sphericity, and thus dwarf planethood. It is also one of only 3 objects known in the solar system, the others being Sedna and 2012 VP113, nicknamed Biden, known to have a perihelion, or closest distance to the Sun, beyond the gravitational reach of the solar system's known planets, and thus no apparent origin for their gigantic orbits. If you watched my video on Planet 9, you will know that it was the discovery of Sedna and its seemingly impossible orbit that led to the proposal of Planet 9 in the first place. Of those 3 paradoxical objects which the poetic souls of the astronomical community have deigned to christen sednoids, which makes them sound like benign tumors, the Goblin is both the closest, with a perihelion of 65 AU, and the farthest, with an aphelion, or farthest distance from the Sun, of 2000 AU, which, though far, is not the farthest aphelion measured for any trans-Neptunian object. But perhaps the most notable thing about the Goblin is that it fits snugly into the cloud of similar orbits first calculated by Konstantin Batygin that showed that something must be corralling the most distant objects in the solar system. The Goblin may not prove Planet 9, but its voice has been added to the ever louder call for its existence. In December, the same team announced the discovery of an object that was, if anything, even more confusing. 2018 VG18, nicknamed Far Out for reasons that will soon be obvious, is a pink, dwarf planet-sized object found at 120 AU from the Sun, the farthest distance at which any solar system object has ever been observed, beating the previous record holder, Eris, by a full 25 AU. But, as the previous paragraph hopefully made clear, the fact that it is far out is not what makes this object so baffling. Rather, it is its perihelion, which is 21 AU, or just grazing the orbit of Uranus. How such a gigantic object could have maintained such a ridiculous orbit over the age of the solar system without being knocked out by Neptune is currently bending astronomical minds. To quote Mike Brown when I asked him on Twitter, quote, "I'd say at this point we have absolutely no idea," unquote. To be fair, far out's far in has yet to be precisely calculated, so it may simply be a matter of more observations. As astronomers have said since the dawn of time, we shall see. The final denizen of the dark edge of our solar system I would mention isn't actually a new discovery. It isn't even a particularly distant object. It is, in fact, a Plutina, a member of Pluto's exclusive club of Neptune-dodging Kuiper Belt objects. What makes it so special wasn't noticed until January of this year, when a team led by Wesley Fraser of the University of Belfast took multiple snaps of its spectrum and realized that, while it may very well act like a Kuiper Belt object, it is, at heart, an asteroid. In fact, it bears a strong resemblance to C-type asteroids, similar to 10 Hygeia, and also to carbonaceous chondrites, among the most primitive of all meteorites found on Earth. This discovery reinforces evidence found from the study of comets that the early solar system was a blender, with material from the inner edge of the solar system cast to the farthest regions, possibly by a migrating planet. This anonymous rock may be a piece of our world's original construction material. Unsacred cows. People tend to forget this, but science isn't about what we know, but about what we don't. No scientist worth his or her proverbial bosons would waste time reciting facts, figures, and inferences drawn from them as if they were holy writ, though this is how science continues to be taught in schools. A scientist is someone who eyes these facts, figures, and inferences like a vulture, poring over them to see if they still hold up, and continuously prodding their weak points until they collapse. This is particularly true whenever stars die, and we are left to pick up the pieces of these complex, bewildering events. In June, Stephen Smart of Queen's University Belfast observed what he thought was a minor stellar flare in our own galaxy, but then realized it could only have originated in CGCG 137068, a galaxy 60 megaparsecs, or 200 million light-years from our own. That meant it had to be very, very bright, the death of a giant star, a supernova. Except it wasn't acting like a supernova. Supernovae rise to their peak brightness over weeks. This supernova, called AT 2018 COW, or the Cow, reached its peak in a matter of days. It was also 10 to 100 times brighter than a normal supernova. And keep in mind that supernovae outshine entire galaxies and can be seen across the universe. These are the sorts of events that astronomers live for. Within days, 24 major telescopes were observing the Cow concurrently. Whatever it was evolving too rapidly to be powered by the standard trigger of a supernova. Of all things, the radioactive decay of nickel. Usually, the aftershocks of a supernova are relatively low-frequency pulses generated by high-energy ions gradually spiraled outward by the dead star's slowing magnetic field. But this star wasn't going that quietly into the night. The pulses remained at high frequency for weeks, indicating that they must be powered by some unseen engine, perhaps an accreting black hole or a raging neutron star. It has been speculated that this may be normal. It's simply that it's usually masked by the cloud of ejecta that forms after a supernova.
This supernova may be the first ever seen completely stripped bare.
Outside of our solar system, there are few phenomena in the universe more important to humanity than Type 1a supernovae. A Type 1a supernova is a stellar explosion that only occurs in systems in which a white dwarf orbits a larger star. These are surprisingly common. In fact, the brightest star in the night sky, Sirius, is in just such a relationship. Thankfully, Sirius and its pup are too far apart to go through this particular spat. In systems where the white dwarf orbits closer in, it will accrete material from its larger, still-living sibling, piling on the pounds until it reaches the magical number of 1.44 solar masses and explodes. Because all Type 1a supernovae explode at the exact same mass point, they all possess almost exactly the same brightness, which is what makes them so important. Catching the telltale signature of a Type 1a supernova from a galaxy far, far away is one of the great quests of astronomy, since, because all Type 1a supernovae are equally bright, by measuring how bright one appears from Earth, you can determine how far away it is, and thus how long its light has taken to reach you, and thus how old the universe is. Humans owe much of their current understanding of their place in the universe to Type 1a supernovae. Which is why the Ohio State University's All-Sky Automated Survey for Supernovae, or ASSASSIN, is making a stir. This year, two of the survey's targets, called Assassin 16BT and Assassin 18OH, have forced astronomers to rethink the processes by which Type 1a supernovae can occur, and in the process, complicated our understanding of where and when we are. Assassin 16OH was detected in the Large Magellanic Cloud, the closest galaxy visible to the naked eye, and location of 1987A, the closest supernova since 1604. So why didn't you hear about it? Well, because technically it wasn't a supernova. 16OH was a super-soft X-ray emission, a phenomenon believed to result from nuclear fusion occurring on a white dwarf surface. Basically, the slow roast to a Type 1a's oven fire. These roasts often result in supernovae, or at least in simple novae, surface explosions nowhere near as powerful as supernovae. But what the team was seeing was nothing like either of them. In fact, it was nothing like any previous super-soft X-ray emission. Its point of origin was far smaller than the surface of a white dwarf, and it displayed none of the phenomenon's secondary signatures. They concluded that the emission had to be formed by some new process, possibly accretional heat, but not directly tied to a future Type 1a supernova. This meant that there is more than one way to produce a super-soft X-ray emission, and thus that our understanding of the finer processes underlying the formation of Type 1a supernovae is incomplete. Not a game-changer, perhaps, but a reason to be vigilant. If Type 1a supernovae are our lights into the universe, then it helps to see them in high res. As such, one of the prime goals of astronomy is to catch a Type 1a supernova in the act, so that the finer details of the event can be properly scrutinized. And that's exactly what happened in February this year, thanks to Assassin 18BT, the first Type 1a supernova confirmed from the Kepler dataset. Unlike 16OH, 18BT is not nearby. In fact, its distance from Earth is a full 53 megaparsecs, in an old dwarf galaxy named UGC 043780. Thanks to a confluence of well-known telescopes, including the Keck, Pan-STARRS, Atlas, and a host of others, the team were able to catch a strange additional emission as the white dwarf gathered itself for its big moment. Attempts to explain this emission have failed to account for everything observed. It may be yet more evidence for an idea that has been gaining ground for the last few years, that there are two different types of Type 1a supernova. Will we have to rethink one of the most cast-iron methods in an astronomer's toolkit? It's unlikely that these two populations have vastly different origins, but we will still have to take them into account as we attempt to map the universe. Barnards Star Bee. Except I already made a video about that, so let's look at some other exoplanets. First, let's look at CI Tory B. And yes, I'm aware that that sounds like the title of a Disney Channel cop show. Just go with it. CI Tory B was actually found a few years ago, but caused such a stir that this year, a team of Cambridge astronomers using the Atacama Large Millimeter Array, or ALMA, decided to look at it again. And what they found only made it weirder. CI Tory B is a hot Jupiter, a giant Jupiter-like planet orbiting its star at distances closer than Mercury is to our Sun. This in itself is nothing strange, at least not these days. Hot Jupiters form the majority of the first planets found around fusing stars. Except that CI Tory is a T Tauri star. That's just a coincidence. The type specimen of this star happens to be in the same constellation. A T Tauri star is a very young star that is not yet contracted to the point of fusion, basically a baby. Stars are believed to remain in this state for just 2 million years, far shorter than the 3 to 10 million years predicted for gas giants to form. Also, hot Jupiters are supposed to form farther from their stars, where material is more plentiful, and then migrate inward to their current positions. A remarkable feat to accomplish in less than 2 million years. ALMA's finding this year only added to the confusion. Like all young stars, Ci Tauri is surrounded by a circumstellar disk, a ring of dust about as wide as the distance to Pluto, that is in the process of being cleared into planets. Within this disk, the ALMA team identified 3 large gaps, likely the cleared neighborhoods of 3 young planets, 2 roughly the size of Saturn, 1 roughly the size of Jupiter.
One giant planet around such a young star was weird enough. But 4?
This backs up work from earlier this year that shows that planet formation begins even before a star is fully formed. It's possible the other planets may have played a role in pushing Ci Tauri B to its current position. But as yet, the mystery of the system remains unsolved. 2018 also brought a host of new results concerning TRAPPIST-1, the gold mine system of 7 Earth-like planets found in February of last year. In January, a paper by Amy C. Barr and colleagues determined that, with the exception of C, the densities of every one of TRAPPIST's worlds are low enough for water to comprise a vast portion of their makeup, likely meaning that they have oceans hundreds of miles deep. B and C are close enough to their star to experience intense tidal force, meaning that they likely experience vast amounts of volcanism. But even D, E, and F experience tidal forces 20 times higher than Earth. It concluded that planets D and E are the most likely to be habitable, assuming they can avoid runaway greenhouse effect. In February, a further series of results derived an approximation of their masses from their gravitational effects on each other. This allowed astronomers to attain their densities, which suggested that the planets were mostly made of rock and that water made up around 5% of their mass. Still an astronomical amount compared to Earth's 0.2%, but less than the 50% predicted by some other models. The study showed that B and C are likely to be similar to Venus, baked hell worlds, while D is estimated to have only 30% the mass of Earth and thus is unlikely to possess a substantial atmosphere. Again, it seemed TRAPPIST-1e appears to be, in size, density, and solar influx, the closest to Earth. But in a system like TRAPPIST-1, as the paper published in October noted, habitability is not as strict as it would be in our system because, given the TRAPPIST planets' proximity to each other, it would be easy for life that formed on any one of them to travel to and infect the others. In November, however, a team from the University of Washington constructed a climate model that suggested that, with the exception of TRAPPIST-1e, all the planets in the TRAPPIST system were either hell worlds like Venus or frozen like Mars. Of course, none of this is known for certain. We'll have to wait for the James Webb Space Telescope to tell us more. Finally, I'd like to end on an exoplanet of no significance whatsoever, except, perhaps, for me. 40 Eridani is a 3-sun system located 16 light-years away from Earth. Its main star, now called Keed by the grace of the IAU, is a K-type dwarf slightly cooler and older than our Sun, orbited by a white dwarf and a red dwarf. And it was this system that Star Trek creator Gene Roddenberry ultimately chose as the home system for the planet Vulcan. He had originally favored the better-known Epsilon Eridani, but backed away upon learning of that star's relative youth. I'd like to say that the discovery of a planet around 40 Eridani A announced this year is a step in the path to fulfilling my childhood dreams, but unfortunately, 40 Eridani AB is a gigantic super-Earth 8 times Earth's mass in a roasting 42-day orbit that makes Mercury's look sluggish. That doesn't preclude the possibility of another planet farther out, of course, so fingers crossed. Gotta say, if the Vulcans do exist, they must get some fantastic sunsets.